Now we will examine the different elements that are involved in heat transfer. Heat transfer is a transfer of heat from a hotter body to a cooler body. Heat transfer is the transmission of heat from a hot region to a cooler region. The candle is the hot region. The piece of rod or metal is obviously the cold region. Observe closely how heat is transmitted by the neighboring particles. This is a type of heat transfer that is specifically called conduction or conduction heat transfer. So, conduction heat transfer. Heat transfer via conduction is very efficient in conductors. An example is metal. So, heat transfer via conduction is a transfer of thermal energy or thermal kinetic energy, which is heat, between solid objects, for example, the road and the tire. Heat transfer via conduction are poor in insulators. Examples are air and space. Thermos bottles are built with double wall containers. The air between these walls are removed during the manufacturing of these bottles. So the condition is now very similar in the outer space. It is a vacuum. Heat from the contents such as water or coffee cannot dissipate to the outside environment since there are no molecules that can bridge this heat, also known as thermal energy, that can leak out from the container. So, this is the reason why thermos are very efficient to retain heat and make your coffee or hot chocolate warm throughout the day. This principle is very similar to how our planet insulates that heat from within to allow the natural geological processes to continue to work for the next several billions of years in the future. So there is a concept called Fourier's Law, and Fourier's Law states that the rate of heat transfer through a material, in the case of glass, is proportional to the gradient of the temperature. When we speak of gradient, that is the final temperature minus the initial temperature, and in this case the final temperature is much lower than the initial temperature, so in which the temperature moves from the one side of the material to the other side of the material, and also proportion to the area of this material in this slab of glass, for example, through which the heat flows. And so the formula is given by Q, which is the rate of heat. So basically when we speak of rate, that is heat per unit time, so there should be a derivative of time in here, and is equal to the K, which is constant for glass, and dt, but our dt or the derivative of our temperature is negative because, as I've said, that the final temperature is much lower than the initial temperature, and so the negative symbol will be placed there in front of K, divided by the derivative of the thickness of these walls. So that is one formula for Fourier's Law. So we have another way of looking at Fourier's Law by the formula delta Q over delta T, or the change in heat over the change in time. And our change in heat is basically, this is heat over time, is what we call the rate of heat transfer. So because it is divided per unit time, so that's signified by the small letter t in there, and that is also multiplied by the K subscript T, which is the thermal conductivity of that material, so whether it's a concrete or glass So there is that material conductivity or thermal conductivity of the material multiplied by the area or the area of that slab or the wall, for example. So that is perpendicular. The heat is perpendicular that crosses through the section of the area of that material multiplied by the temperature gradient, which is the final temperature minus the initial temperature, and usually by default that is negative because heat transfer from a hotter body to a lower temperature body. That is overall divided by the thickness of the slab. Okay, so that is the formula for Fourier's law, and here are some useful thermal conductivity conversion factors. This is a table of the different thermal conductivity of the different materials, and you can notice the difference between the value of thermal conductivity between a foam, which is the polyurethane foam PU, and also the thermal conductivity value for concrete. So foam is a good insulator because it is filled with gas bubbles, and gases conduct heat less effectively as compared to their solid counterparts such as concrete. And because of high thermal mass, concrete also absorbs heat from the atmosphere, especially in warm weathers or especially during summer season. And these heat are stored and are released at night, creating the phenomenon called thermal flywheel effect. Here is a problem that will use the formula of Fourier's law. An iron plate is 2 centimeters in thick and it has a cross-sectional area of 5,000 centimeters square. One face of this iron plate is at 150 degrees centigrade, and at the other side is 140 degrees centigrade. The question is how much heat will pass through this iron plate in every second. And for an iron plate or iron, it will have a thermal conductivity value of K subscript T, which is equal to 80 watts per meter Kelvin. And the formula to get the amount of heat that passes through the plate in every second is the change in heat over time. And that will be equal to K subscript T multiplied by the area times the change in temperature delta T over the thickness, which is L. And we will be making use of all these values to replace in the formula that we have for Fourier's law. K subscript T is 80 watts per meter Kelvin multiplied by the area, which is 5,000 centimeters square. But since we are making use of meter, we will convert this 5,000 centimeters square into its equivalent meter square, and that would be only become 0.50 meter square. Now, for the change in temperature, the formula is final temperature, which is 140 degrees Celsius, minus the initial temperature, which is 150 degrees Celsius, will become negative 10 degrees Celsius. But the negative sign is already placed before. However, we are also making use of Kelvin, and the change in temperature is only degrees Celsius. Therefore, we are going to convert the Celsius into Kelvin by adding 273 so that Celsius will now become Kelvin, and later on Kelvin unit can be cancelled out. And that will be divided by L, which is 2 centimeters, again be converted into meter, so that is equal to 0.02 meter. And to solve for the problem how much heat passed through the plate in each second, this will be calculated, and the answer is equal to negative 20 kilojoule per second, or just simply 20 kilojoule per second to answer the problem about the amount of heat that passed through the plate per second. So we have two metal plates. They are soldered together, and it is known that the area of the two plates is equal to 80 square centimeter. So both plates will have the same area, that is 80 square centimeters. Now for the thickness, for plate 1 will be having the same thickness with plate number 2, and that is equal to 3.0 millimeters. Now T1, which is located in this section, is equal to 100 degrees centigrade, while T2 will be in the opposite side of the second plate, which is 0 degrees centigrade. For the plate on the left, which is this one, will have a thermal conductivity value of 48.1 watts per meter Kelvin, while the plate on the right, which is this one, will have a value of 68.2 watts meter Kelvin. Now the question is, find the heat or flow rate through the plates and the temperature T at the middle where the junction or the solder junction can be found. So that will be our main question in here, and there is an assumption that we assume an equilibrium condition so that the heat that is flowing through plate 1 will be just equal to the heat that is flowing through plate number 2. Now we equate the two Fourier's Law formula for the two plates because the heat flow rate that pass along plate 1 is also equal to the heat flow rate that pass along plate number 2. So the Fourier's Law for plate number 1 is given by the formula K subscript T1 multiplied by the area of plate 1 times T1 minus T, and T in here is the temperature along the welded junction, divided by the thickness of plate number 1, which is also equal to the flow rate in plate 2, and that is K subscript T2 that designates to plate number 2 multiplied by area of plate number 2 times T, which is the T at the junction, minus T2 over the thickness of plate number 2. Since the thickness of plate number 1 is also equal to the thickness of plate number 2, that can be cancelled out. Area 1 is also equal to the area of plate number 2, that can also be cancelled out. And so the new form of our equation would give us K subscript T1 times T1 is 100 degrees centigrade minus T, which is the temperature at the junction of the welded plates, is equal to K subscript T2 times T, which is the temperature at the junction, minus 0, which is the temperature of the plate number 2 in the other side. Now, in order to get the value of T, we are just going to isolate this and transpose all the values and the equation of the other side. And so we are able to get the value for T, which is equal to 41.4 degrees centigrade. We can substitute this value in either this formula or in this formula. And in this case, we are going to make use of the flow rate for plate number 1. So that is the flow rate, which is equal to delta Q over delta T, which is equal to K subscript T1. And K subscript T1 is equal to 48.1 watts per meter Kelvin, multiplied by the area, which is equal to 80 centimeters square, and that will be converted into meters square, and the value would be 0.0080 meters square, multiplied by the change in temperature, which is T1, that is equivalent to 100 degrees centigrade, minus T, which is the temperature at the junction, which is now computed as 41.4. But since they are still in Celsius, that will be converted to Kelvin. And that will be divided by the thickness of plate 1, which is 3.0 millimeters, but converted to meters, that is equivalent to 0.0030 of a meter. And therefore, the flow rate, which is also equal to the flow rate of plate number 2, the value would be 7.5 kilojoule per second. Heat transfer via convection. The heat transfer via convection is actually a transfer of the thermal kinetic energy, also known as heat, between moving particles such as water, air, including magma. Convection is the transfer of heat between two bodies by currents of moving gas or fluids. Earth's convection currents are the heated mantle material that is slowly rising from deep inside the planet. The cooler mantle material sinks and the warm rises, creating a convection current. The convective current is responsible for the movements of the plates of the Earth's crust. The heat convection equation is given by the formula Q subscript H, that is the heat flow in watts. That is equal to small letter h, which is heat transfer coefficient in watts per square of a meter degrees Celsius. A is the area of the conducting fluids in square of a meter. And T2 minus T1 is the temperature difference in degrees Celsius. Supposing we have air conditioning units that are releasing heat into the ambient temperature, which is 28 degrees centigrade, and the heat is equivalent to 58 degrees centigrade. So what will be the heat transfer from the air conditioning unit to the ambient atmosphere? So that will be the amount of heat that will be removed from the air conditioning unit. And supposing if the coefficient of heat transfer due to convection is equal to 6 watts per meter square degrees Celsius. So basically this is the coefficient of heat transfer of air. And the formula for getting the or determining the heat transfer value is equal to Q subscript H is equal to H, which is the coefficient of heat transfer, that is equivalent to 6 watts per meter square degrees Celsius, multiplied by the area, and we assume that the area is 1 square meter, and multiplied by the change in temperature, so that is 58 degrees centigrade minus 28 degrees centigrade, and so that will be 30 degrees centigrade. So the value is equal to 180 watts. So this is the amount of heat that is released into the ambient air, or also equivalent to negative 180, which is the heat that was dissipated by the air conditioning unit. Now finally, the heat transfer via radiation. An example to the heat transfer via radiation is the heat of the sun. Radiation is a kind of heat transfer, that is the energy that is emitted by matter in the form of photons or electromagnetic waves. So basically, radiation is a transfer of the thermal kinetic energy or heat across space. It do not require fluid or contact. So the transfer of heat through space is through electromagnetic radiation. They do not require contact or movement of particles. However, radiation can be reflected by shiny objects. Example is roof insulator. Shiny surfaces are poor absorbers and emitters of radiation. So instead, they are used as insulators. An example is to preserve food heat and at the same time to minimize heat of radiation from our roof to enter into our homes. But radiation can be absorbed by dark bodies. And there are two concepts about dark bodies. One is black body. Black body is an ideal body that absorbs fully all the radiations, and it can also emit back all the radiations away from itself. This is actually not existing in reality. However, this is made for computational reference only. A black body is an ideal body that can absorb all electromagnetic radiation. It is a perfect absorber and a perfect emitter of radiation, while the actual is called a gray body. A gray body is the actual object that cannot absorb all the emitted radiation. It is also not a perfect absorber and it radiates at a lesser amount than what is absorbed. This is also known as an opaque object. This is now the formula for heat of radiation. P is equal to epsilon, where epsilon is the emissivity of the surface, while A is the area and sigma is the Stefan-Boltzmann constant, while T raised to the power of 4 is the temperature in Kelvin. A spherical body of 2.0 cm in diameter is maintained at 600 degrees Celsius, assuming that it radiates as if it were a black body. At what rate in watts is energy radiated from the sphere? So this is the black body with a 2.0 diameter maintaining at 600 degrees centigrade. So the area or the surface area can be calculated from the formula 4 pi r square, where 4 times pi and the r is 2 divided by 2, that is equal to 1, and converted into meter, that becomes 0.01 meter raised to the power of 2, so that the surface area will now be equal to 1.26 times 10 raised to the minus 3 meter squared. And so the formula P is equal to alpha times sigma times the temperature raised to the power of 4. And so the area now is 1.26 times 10 to the minus 3 meters square times the sigma, which is the Stefan-Boltzmann constant 5.67 times 10 to the minus 8 watts per meter square Kelvin times the temperature plus 273, so that we will be able to convert Celsius into Kelvin, and that is 873 Kelvin raised to the power of 4, and so the emitted heat of radiation is 41 watts. An unclothed person whose body has a surface area of 1.4 square meter with an emissivity value of 0.85 has a skin temperature of 37 degrees Celsius and stands in a 20 degrees Celsius room. How much energy does the person lose per minute? Take note that the temperature here, which is 37 degrees, which is the temperature of the person, is always added with 273 to convert everything into Kelvin, and the temperature of the surroundings, which is 20 degrees centigrade, will be also added by 273 so that we can get 293 Kelvin. So everything will be converted into Kelvin. The formula P is equal to emissivity times the area times the Stefan Boltzmann, that is constant, multiplied by the change of temperature, which is the temperature of the person raised to the power of 4 minus the temperature of the environment raised to the power of 4. And so this time we have to consider the energy loss within 1 minute. Therefore, we are going to add the symbol delta T, which is the amount of time that the energy loss is within the period of time. And so, carrying the formula, adding the delta T or the change in time, and so therefore emissivity is equal to 0.85 our area, which is 1.4 square meter, multiplied by the Stefan Boltzmann, which is later on we'll substitute with 5.67 times 10 to the minus 8 watts per square meter times Kelvin raised to the power of 4, multiplied by the change of temperature times 60 seconds. And so again, substituting the value for Stefan Boltzmann, which is constant, and so we will get the value of 7.6 kilojoules, or equal to 1.8 kilocalories, which is the energy that is lost by the person within 1 minute.